The next culture we're going to study is Egypt. And the Egyptians had these papyrus that they wrote on, and they weren't as durable as the Babylonian clay tablets. But we still do have a lot of Egyptian math that we were able to figure out what their algorithms were and what their math was. This Egyptian math goes back around the same time as the Babylonians in like 1600 BC. And the things I want to show you in this lesson, first I want to show you their multiplication algorithm. Because the Egyptians were very good, even though they didn't have a great number system, the thing they knew more than anything that they were able to utilize was the ability to double numbers and to double numbers and to take halves of numbers, and also to take 2/3 of numbers. So let's say that's a skill we have, and we're not going to use the Egyptian number system at all until we get to fractions. So first thing I want to show you is how to do a basic multiplication. For instance, 23 times 21. The way we do this is we make a little chart, a 2-column chart. And in the first row, we put the number 1, and then the thing that we're multiplying. So 23 times 21, we put that 23 over here. They think of 23 times 1 as different than 21 times 23. That one, they would make their chart have a 1 and a 21 first. Okay, now what they do is they double the numbers in each row. So 1 becomes 2, and 23 becomes 46. Now the next row is not 3, like a times table, but it doubles. So double 2 is 4, double 46 is 92. And we keep doubling, 184. And we double again, 16 to 368. And we stop when our next doubling would cause this number on the left to be greater than 21. So I'm not going to make another thing, because that would get me to 32, which is bigger than 21. Now, we look and try to find the numbers on the left that add up to 21. And those are 16, which we put a check next to. 16 plus 4 is 20, plus 1 is 21. And you'll always be able to, if this thing on the right is an integer, these numbers here are always going to be powers of 2. So it's always going to be possible to find numbers that add up to 21. What I like to do is take the number that's closest to the biggest number that's less than 21, which is 16. If you want, you could even say 21 minus 16 equals 5. So 16 got used. Then you look for the biggest number that's less than 5, which is 4. You could do 5 minus 4 is 1, and then finally the 1. So even if this 21 was a very large number, and this is a bit related to like what we learned in binary, where 21 is a 16, no 8s, a 4, no 2s, and a 1, but that's just a real modern interpretation of that. You can write any number as the sum of powers of 2, and in this case 21 is 1 plus 4 plus 16, I'll write it like that, equals 21. Well, now the corresponding numbers by these check marks are 23, 92, and 368, and on the side we add those together. 23 plus 92, and that equals 483, which is the answer. 23 times 21 is 483. So the skills that they needed were being able to double numbers they needed to be able to figure out what numbers add up to 21, and they needed to be able to add these numbers together. Now, why this algorithm works? Well, 23 times 21 is the same thing as 23 times 1 plus 4 plus 16. And then if we imagine like a distributive property, that's 23 times 1 plus 23 times 4 plus 23 times 16. And that's exactly what we end up doing over here. If you wanted to practice doing it the other way, well, that would look like this: 2, 42, 4, 84, 8, 168, 16, 336. Add up to 23, that would be 16. I still need 7 more, so 4, 2, and 1. And then I would add together these 4 numbers. And I should end up, so I'll actually go here and say 23 is 1 plus 2 plus 4 plus 16. And over here I would do 21 plus 42 plus 84 plus 336. And I do get 483 for that answer also. It really wouldn't matter if they're both integers which way you did it, but officially you should put the number that's on the left. That's how the Egyptians would do it. 23 times 21. They would think of it more like 21 groups of 23 rather than as 23 groups of 21. And that's how you do multiplication, and it will always work if the numbers are both integers. The Egyptians also had a division process, which is very similar. So if I wanted to divide 483 divided by 23, I would make another chart, and this chart is definitely, there's no ambiguity, whereas here it's like, should I put a 23 here or a 21 there? For division, there's no ambiguity. You will definitely be putting the 23 there. And then, just like before, you double, you double, you double, you double, and we stop doubling when we notice that if I double the 368 again, it's going to be bigger than the 483. Now, the way we answer the question is we look for what collection of numbers in this list on the right add up to 483. Now that seems like it's pretty hard to do, but let's just assume for now that the answer to this question is an integer. So what you can do is you do 483 minus the biggest number that you have that's on that list. And we can put a check over here, and what's left is 115. Now you look on the list for the number that's the biggest number that there is that's still less than 115, which is 92. And we're going to use that. And then we got pretty lucky there. It seems 23 is right there on the list. So then our answer is what we get when we add together these 3 numbers. And 21 is the answer to this question. Here's another one of those just to do another one. So for this one, I make my chart 14, double, 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 and I'm not going to double again, because if I double the 448, it will be bigger than 602. Now to get 602, I'm going to look on the list for the biggest thing that's less than 602. And on the side, I'll do 602 minus 448, which is 154. Then I look for the number that's less than 154, which is 112, and I subtract that, and I get 42, and 28 is less than 42, and that leaves 14, and that's convenient because 14 is right there. So I'm going to use, on the left, these checks correspond to 1, 2, 8, and 32. And that becomes 43, which is the answer. The Egyptians' number system was a lot like Roman numerals, and they could write, integers that way. But the thing that's most famous about Egyptian math, unlike the Babylonians who had this base 60 system and they had like decimals that helped them write things like 1/8 as like a base 60 decimal, the Egyptians had a type of fractions. And the most famous thing about Egyptian math are their fractions. The strange thing about their fractions, the way they would write their fractions, they would do like 4 with like a 1 with like a little line over it. That was 1/4, and that was 1/2. So they had fractions like 1/4, 1/2, 1/3, 1/5, and they actually had they had a symbol that represented the number 2/3 also. But while they had all these fractions, let's put 2/3 first because it's the largest of them. They did not have a concept of how to, they didn't have a way to represent a number like 3/4. Like I said, 1/4 was written like this, so it wasn't officially like a denominator, but it was representing the concept of 1/4. But if they wanted to express the idea of 3/4, you might say, okay, well, why not just write, 1/4, 1/4, 1/4, like 3/1/4. But that's not how they did it either. Instead, they did something that seems really odd to us nowadays. But they would write their fractions as sums. By the way, these are called unit fractions. Anytime a fraction has a 1 in the numerator. So they would write it as sums of unit fractions, but they had to be unique. So they couldn't write 1/4, 1/4, 1/4, but instead they would write 1/2, 1/4, which is implied that there's like a plus sign between it. It's pretty hard though. Like if you think, okay, 3/5, if I have to write that as a sum of fractions with a 1 on top, what would they be? I can't say 1/5 plus 1/5 plus 1/5. Well, there is a process that I'm going to teach you for doing this. But for now, let me just tell you that 1/2 plus 1/10, if you don't believe it, is 5/10 plus 1/10, which is 6/10, which is 3/5. So when they wanted to express the idea of 3/5, they would say it's 1/2, 1/10. That's their way of expressing the idea of 3/5. Now this seems like an unusual way to represent fractions, and pretty cumbersome. In fact, it's not even unique. Sometimes there's more than one way to write a fraction as a sum of unit fractions. But there's a nice explanation I've seen, which is like this. One of the questions in a famous document called the Rhine Papyrus says, how to divide 6 loaves of bread among 10 men. And nowadays we know that each person would get 3/5 of a loaf of bread, although they would call it 1/2 plus 1/10. They wouldn't put the plus sign. And let's see why that is. Why is 1/2 1/10 in any way better than just 3/5? Well, if you actually have the 6 loaves of bread represented by these rectangles, and you try to give each person 3/5, what would happen is I can give 6 people 3/5, but then the other 4 people, well, they have to get a 2/5 piece So those 4 people each get one of these 2/5 pieces. Plus, if we take this other 2/5 and split those up into 1/5 each. So 4 of the people get nice big, 6 of the people get nice big 3/5 loaves, whereas the other 4 people get a 2/5 and a 1/5, and this guy gets a 2/5 and a 1/5, and this guy gets a 2/5 and a 1/5. And this guy gets a 2/5 and a 1/5. And yes, they all got 3/5 loaves of bread, but maybe the people who have 2/5 and 1/5 are either they don't believe they got the same amount of bread because it doesn't look exactly the same, or they just didn't want it in 2 pieces for whatever reason. Well, if instead we think of it as 1/2 1/10, it allows us to do something like this. So if instead of giving people 3/5, literally 3/5, I give them 1/2 plus 1/10, which is equal to 3/5, then I can give each person, like this person could get a half. If I split up the 5 loaves into halves, so all 10 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, get a half. And then I split the last loaf into 10ths each. And then this person, the red, gets a half and a 10th, and the orange gets a half and a 10th, and so on. So not only does everyone get the same amount of bread, but they get the same sort of division. Everyone's got a half and a 10th, so nobody can be jealous of the other person who got their 3/5 in a different way. So that's like a theory about why they might have done it this way. I mentioned before that these unit fractions are a bit confusing because 3/5 could be written as 1/2 plus 1/10, but here's another representation of 3/5. 1/3, 1/5, and 1/15. If you don't believe it, change these into 15ths. This would be 5, 3, plus 1, which is 9 over 15, which is 3/5. So it's not even unique, which makes it, even more complicated. The Egyptians, though, were very, because this was their system and they got used to it, they, for instance, would just know right away when they saw these two things that they would equal each other, that 1/2 plus 1/10 is equal to 1/3 plus 1/5 plus 1/15. This is not something that people know about nowadays, but they would know that. Like another thing they knew is that 1/3 is, sometimes you can even take a unit fraction like 1/3 and split it up into unit fractions. Now, it's important, one of the decomposing fractions into unit fractions is a tricky thing, and I'm going to, at the end of the video, show you some methods of this. And if you're in the math major class, you'll want to watch that. But if you're in the afternoon class, that math teacher class, you won't have to study that part. But that'll be at the end of the video. I'll tell you when that happens. In the most famous mathematical Egyptian artifact, which is called the Rhine Papyrus. Rhine Papyrus is a collection of, I think, 83 problems, plus it has a table in the beginning. And that's where we know most of our information about Egyptian math. They have something called the 2/n table. What the 2/n table is a way of taking all the fractions that have odd denominators and writing them as a sum of unit fractions. And this idea that 2/3 is 1/2 plus 1/6, that's like a fundamental truth. And I told you 2/3 is actually the only fraction that is a fundamental fraction for them that they have a special symbol for. But there is actually a way to split up 2/3 into 1/2 plus 1/6. And 2/5, just to give you a couple, 1/3 plus 1/15. And 2/7 is 1/4 plus 1/28. There are multiple ways to do this. Sometimes it's pretty complicated. Like 2/13, there are various ways. The way that's on the chart is 1/8 plus 1/52. I put the pluses, they don't. Plus 1/104. And they don't do evens because 2/4, if it's got an even denominator, you could just reduce it. So the 2/n table has everything from 2/3 all the way up to 2/99. And here's what that looks like. And you should print up a copy of this. If you're in my class, there's a handout for this, or it's on the Google Doc. If you're not in my class, you're just watching this video, you can screenshot this or put it in another window. But this is the 2/n table. And the 2/n table is very useful because it can be used if I want to multiply something that's not an integer by something that is an integer. So let's just look at an example. Let's say I want to do 3 1/5 times 11. For this lesson, I'm going to have the fraction here on the left and the integer on the right. So remember, I go like this: 1, 3 1/5. Now I double each side. Well, this becomes 2. Well, when I double the 3, it becomes 6. But when I double the 1/5, it becomes 2/5. But there is no number for 2/5. So I go back to the chart and look up 2/5, and I see 1/3, 1/15, and that's what I put here. Now I'm trying to get to 11. So I double the 2 and get 4. This 6 becomes 12. The 1/3 actually can become 2/3. I don't have to look up the 2/3 thing. Sometimes they might. Sometimes they found it better for whatever situation to actually turn 2/3 into 1/2, 1/6. But in general, I'm not going to do that. Now this 1/15 has to become 2/15, and for that I can look that up, and that's 1/10, 1/30. So this number is getting pretty ugly looking. I just need to do this again. So 8. Now the 12 becomes 24, but they knew very well that 2/3 doubled was 1 1/3. So this would be actually the 24 plus the 1 1/3. Actually, I'm going to go like this: 24, 1 1/3. 1/10 becomes 2/10, which becomes 1/5. You see, doubling a fraction with an even denominator, you just divide the denominator in half. And 1/30 becomes 1/15. I'm going to write this as 25 1/3, 1/5, 1/15. And I don't need to double this again because it would get to 16 here. Just trying to get to 11. So 11 is 8 plus 2 plus 1. And now, this will look pretty ugly, but I'm going to combine these three things just like I did before with multiplication. So the 24, the 6, and the 3, that's 33. And as far as the fractions go, sorry, it was 25 because of this. So this is 34. 25, 6, and 3 is 25 plus 9, that's 34. And I'm just going to write all the fractions next to each other for starters. So I'm just going to write 1/3. I'll write the biggest fractions first. So there's the 1/3. Here's another 1/3. Here's the 5th from here. Here's the 5th from there. There's a 15 here. And there's a 15 there. And I'm going to simplify this a little. I can simplify the 1/3 and 1/3. I can write 2/3. The 1/5 and 1/5 is 2/5, which I need to come back here, and that becomes, so this 2/5, I look up again back on the 2/5, it's 1/3 plus 1/15. And these 2/15ths, I look up 2/15ths, that's 1/10, 1/30. And finally, I can take this 2/3 and 1/3 and put that together to become 1. So the whole answer becomes 35. I like to write the fractions biggest to smallest. 1/10, 1/15, 1/30. For our purposes, we'll leave the answer like that. Although, just so you know, the Egyptians were really aware that 1/2 plus 1/3 plus 1/6 was equal to 1. That was a thing that they were really good at knowing. So they would have recognized that 1/10 plus 1/15 plus 1/30 is kind of like 1/5 times 1/2, 1/3, 1/6. And they would have actually replaced this whole thing with 1/5. But that's asking students a lot to like recognize certain of these things. But that's how they were really adept with these. For our purposes, I would expect you, if you had to do this question, 33 1/5 times 11, you can follow all these steps, and you follow all these steps and end up with this answer. In the Rhine Papyrus, at one point, they have all these questions about dividing loaves of bread, and also when they divide 7 loaves of bread among 10 men, they find that 7/10, we'll learn how to do this in a future lesson, but here's just a fact for you, that 7/10 does equal 2/3 plus 1/10. So let's just say, we have the 2 over n chart, we don't have like a 7 over n chart, so I'm telling you right now that 7/10 is 2/3 plus 1/10. If you don't believe it, get common denominators. 20 over 30 plus 1 over 30 equals 21 over 30 equals 7 over 10. And we do learn how to actually find this calculation, but we can test that the answer is right by doing 2/3, 1/10 times 10 and seeing if I get 7 to sort of verify that it's right. So I'll say 1, 2/3, 1/10, double it. 2/3 doubled is 1 1/3, so they write 1 1/3. 1/10 doubled is 1/5. Double it again. This becomes 4. This becomes 2 2/3. But to double 1/5, I have to go to my chart and get 2/5, which is 1/3, 1/15. Oops, this is actually a 30 here. Sorry about that. So that means that this was a 30. And that means that this is 1/15. When you double if it has an even denominator, you just take half of that. So 1/15, that becomes 2/15 is 1/10, 1/30. And now I do 8. That 8's the last one I'm going to need because I'm trying to get times 10. So this becomes 2 times 2 becomes 4. 2/3 doubled is 4/3, which is 1 1/3. That's why this is 5 1/3. 1/10 doubled becomes 1/5. And 1/30 if doubled is 1/15. So now to get 10, I need this line and this line to add together. So the 5 plus the 1 becomes 6, and this third becomes 2/3. And this 1/5 comes here, and there's a 1/15 and another 1/15. So those two become 2/15. But again, 2/15 is 1/10 plus 1/30. Now we could leave the answer like this. I mean, you could kind of go modern for a second and just add these three things together and notice something interesting happens. If I get a common denominator of 30, this is 6 plus 3 plus 1, which becomes 10 over 30. Which is 1/3. So this actually does become 7, that 1/3 together with the 2/3. They would be very aware of this 1/5, 1/10, 1/30. Remember before I said they were extremely aware that 1/2 plus 1/3 plus 1. Sorry, forget that for a second. They would be very aware that 1/5, 1/10, and 1/30 together was 1/3. That's just a thing that they would be really familiar with. So they would be able to continue this question. But I'm not asking you to memorize these sort of esoteric facts about what unit fractions add up to other unit fractions. So you could leave it like this and then just kind of do modern common denominators to just see that it did become 7. Just another thing I'm going to quickly mention. This 1/10, 1/30 is actually on the chart here as 2/15. So they might notice that and say, well, so they would kind of recognize this as 2/15. And 2/15 plus 1/5, which is really 3/15 would become 5/15, which is 1/3. There's a lot of ways that they might know to continue with this problem. But for our purposes, we leave it like this. Or if I'm asking you to prove that it equals 7, you could kind of cheat at the end and just do common denominators and you'll get it equal to 7. Now this is an advanced topic that if you're in the morning class, I want you to be aware of it. If you're in the afternoon class, you can skip this part. Some methods of coming up with these the 2 over n chart. One method is to start with the fact, and they would just know this, that 1/2 plus 1/6 equals 2/3, so that's like a starting point. Well, if you start with that point, you can get any multiple of 3. no reason to do 2/6 because that's the same thing as 1/3. But if I wanted to, I could take half of each of these fractions, 1/4 plus 1/12. Now, even denominators aren't really needed, but 2/9, I could take the 1/2, 1/6, and take 1/3 of each of those, 1/6 plus 1/18. And if you look at the 2/n chart, you will notice that at least for those values, the things that are this entire column actually, the multiples of 3, skipping the even ones, all have this form where it's 1/2 plus 1/6 multiplied by whatever the appropriate number is. Now, not every fraction has a denominator that's a multiple of 3, so there is a technique, like let's say I want to do 2/35. There's something called the greedy algorithm. That's where you take the biggest fraction that you can. Now, 2/35 is a little bigger than 2/36, which is it's bigger than 1/18. So it's 1/18 plus like something. Or, sorry, 1/18. I could go like this also. 2/35 is actually equal to 1/17.5. But that's going to be bigger than 1/18. So I could say it's 1/18 plus something. And what is that something? Well, I do a little algebra. 2/35 minus 1/18. And when I do common denominators on that, it gets kind of ugly, but it does become 1/600. 1/630. So 2/35 could be 1/18 plus 1/630, although that is not the best, because it's also equal to 1/30 plus 1/42. Now, how would they have gotten this one? Well, they wouldn't have used the greedy algorithm. They'd have to use some other way. If I look at the actual chart, 2/35, which one did they use for that? They use 1/30 plus 1/42. There's different tricks they have. Like I said, these aren't even unique. So, and some of them are pretty crazy with 4 different fractions. They chose the ones that were best for this chart, but maybe in other situations they might have used other representations. We're going to learn other ways to figure out not just the 2/n chart, but how to, for instance, how to get that 3/5 is 1/2 plus 1/10. We'll see that in the next lesson. Okay, that's it for today.